So we started with talking about, remember, reflection, refraction, total internal reflection, and so on, frustrated internal reflection, all that. And the goal here is to be able to analyze very, very simple optical systems, imaging systems, okay? Of course, you can use imaging systems also to do non-imaging, which we will talk about later on, I think next week. But so we need to understand this well enough in order to apply this for other applications as well. Clearly, one can use a lens to focus light onto a solar cell, right? Very simple solar concentrator. So we should have a good understanding of this part as well. Now, in terms of analyzing simple optical systems, we'll walk through the principles today, basically. And it's fairly straightforward, mostly common sense, right? So we looked at this very simple case where we have air, we have a spherical surface, let's call it glass, and we have a point source. Okay, so light coming out, spherical waves, and it is incident on the interface between air and glass, and it refracts. Okay, so that's what we're trying to analyze in this very, very, very simple example. So you have three things that are happening. We have free space propagation, light propagates from the source to the lens. Then we have refraction at the surface of the lens, and then you have some free space propagation within the lens. Okay, in this particular scenario. A few things that we should keep in mind from last week is that we will assume this angle that the rays make with the optical axis. So this is called the optical axis. That is the axis of symmetry of the system, essentially, because we are assuming circular symmetry here. Okay, so we're looking at a cross-section of a circular symmetric optical system. Epsilon is the angle that the ray makes with the optical axis, and that is assumed to be small. Okay, that's the whole idea of paraxial approximation. As a consequence of that, we will also, what happens is that instead of having a curved interface, we will assume that the interface is essentially a straight line, a plane, which we mentioned last time. Okay, once we make those assumptions, then everything becomes very straightforward. Okay, so before we write the equations, which I think are here, okay, so this we can start. The way we analyze, there are many ways you can analyze optical systems. In geometrical optics, the simplest possible way to analyze is with rays. Okay, now a ray, as we talked about last time, has a direction essentially, right? It has an angle at which it propagates. It can also have a position, right, where it starts from. So if you have a three-dimensional space, you have a position in x, y, z, and a direction. And you can have a direction against several axes, right? X-axis, y-axis, z-axis. For simplicity, we are assuming two-dimensional space here. Either it can be a real two-dimensional space, or it can be just a symmetry, right? Cylindrical symmetry. Okay? So the variables that are of interest here are essentially two things, before we go into that. Is the position of the, so let's say that is the optical axis. The variables that are of interest is the position of the ray at a particular location. So this is z, let's say that's x. This position x. Okay, of course z is also important, we'll come to that. And the direction, right? So the ray has a certain angle. Okay, so the ray can be defined by two variables other than z, and that's what we will do in these calculations. One is position x and one is alpha, the angle. Okay, so the way you monitor what happens to the ray in an optical system is trying to calculate what happens to x and alpha as it propagates. Okay. In other words, what happens to x and alpha when these things happen, essentially. So that's the simple way to think about it. Okay? The mathematics is very straightforward. Okay? So we'll go through quickly. So, of course, free space, so the first part of this is, so that's x naught, let's say it's the starting height of the ray from the optical axis. Alpha naught is the angle, starting angle, let's say, would be correct. What happens is free space propagation to the angle? Nothing, right? It just propagates in a straight line, so alpha naught equals alpha 1. So, okay, so let me make one more So what we are trying to do is develop what's called matrix optics, okay? And I'm not going to pay much attention to the formalism, but that's technically what we're trying to do. And all that means is the following. Okay? You have an input position and angle for array, and you have an output position and angle for array. And you have a matrix that determines what happens to it. And that matrix is different for different things, like free space propagation, refraction at the interface, and later on we'll see passing through a lens, all that stuff. Okay? And this is how most computer programs do it. Obviously, no one actually does these things by hand anymore. It's all done on computer, but you need to have an understanding of what that means. Okay? So that's the goal. So free space propagation, what we're trying to do is that's the input, which is my x naught, alpha naught. That's the output, which is my x1, alpha 1. Clearly, alpha naught and alpha 1 are the same because it's free space propagation, and x1 is just scaled up geometrically, right? It's as simple as that. So from a free space propagation point of view, I forget exactly which one I put first. Okay, I think I did put x1. So from a free space propagation point of view, can you tell me what should go in here? So what happens to x? Everyone knows matrix multiplication, I assume. If not, let's very quickly review it. If you have a matrix, the way you multiply this is you take A, multiply with A prime, multiply and add it to B times B prime, right? Very quickly review, and the same thing, and that will be the answer A. And for B would be C times A prime plus D times B prime, right? You just do, okay. So can someone tell me what should this be? This essentially is telling me, so there are 4 terms that go in here. First term should be what happens to x. How does x vary with x prime essentially, right? Is that
identical times 1.
No, x has changed, right? Remember. Actually, I forget. It should be identical, but yeah, you're right because you can add from here. I think, because I forget now what it is. Oh yes, yeah, that's correct. So you can just add the tangent. So yes, that's 1, but then you need to scale it up by the distance essentially, because we are assuming that the alphas are small. So okay, so I'm going to draw this over here. So I'm going to draw very simple geometry, right? So we have alpha. This is the distance d01, and let's say this is what x1 minus x naught, right? Yeah. So tan of alpha is basically x1 minus x naught by d01. Tan of alpha is just alpha, right? Because alpha is small. So then you get x1 equals d01 alpha plus x naught, and then just make it into matrix. So that's the coefficient for alpha, and 1 is the coefficient for x naught. Right? So this is the distance between the lens and the object. Same thing happens here. Well, similar thing happens here. For the angle, there's no dependence on x prime, right? It doesn't change. It's just free space, so that will be 0. And this is just 1, right? It's the same. So that gives you a matrix transformation for free space. Can you see that? Yeah.
Yes.
Okay. I don't know if you're shadowed by this.
No.
I'm asking.
Thank you.
Okay, so it's very simple, right? Very straightforward stuff. So that's how you do that. And you can do the same thing, and I won't walk you through all of them, so it'll take too long, but you can do the same thing for refraction at the interface. Of course, for refraction, again, you can see it very easily. If you ignore any propagation, then the distance from the optical axis is the same, because it's the same point, right? So x1, in this case, I notated it as x1 prime and x1, n prime and n. So x1 prime is equal to x1, because it hasn't moved anywhere. But of course the angle has changed, right? That's the whole point of refraction. Angle changes by Snell's law, right? And you can work that out by essentially n times n alpha should be equal to n prime times n alpha 1 prime. From that you can figure out what alpha 1 prime is. Okay? Because the normal here is just this optical axis itself in this particular case. Okay, I won't go through the derivation, but then you can make another matrix here, right? So the matrix here, so the matrix on this side, if you, again, what we're trying to do is x1 prime, alpha 1 prime. Right, so this is 1, and that's 0. Right? And for the next one, it's just, what is it? N minus n prime. Right, n prime times r. And this is n over n prime. Now, remember, we assumed the radius of curvature r, which is where the tangent changes. So it's actually not the optical axis. I misspoke. So, okay. So let's draw the spherical surface. So it has a radius of curvature r, starting from some center. And of course, the normal to that point is that, right? So when a ray comes in here, the angle here is alpha, but we actually need to know this angle. That's where Snell's law is applicable, right? So that's, you need to do some geometry to figure that out. And this is the other, sorry. This is the angular refraction, right? But it's not alpha 1 prime, because alpha 1 prime is measured with respect to the optical axis, which is why you need to have some factors for conversion. You can derive it. It's not that difficult. Okay, some geometry. Is that clear? I'm not going to walk you through every single derivation. So just if you have any confusion, let me know. Okay. All right. So if you so we once we have those two, we have propagation, and then we have refraction. Then we can relate the output. Because remember, what we are trying to do here is to express what happens to the ray at the end, inside the glass, after it has done all these three things. Okay? So, of course, the way you do it, which is the nice thing about matrix optics, is you multiply the matrices together. As simple as that. Of course, in matrix multiplication is not commutative, which means if you multiply matrix 1 to matrix 2, it's not the same as multiplying matrix 2 to matrix 1. So the order is very important. Of course, in our case, the order is just from reality. You go through propagation in air first, refraction in air glass next, propagation in glass next, right? So there's an order to what happens in the ray. Okay? So you can propagate, so this last bit is the propagation within the glass. So it's the same thing as air. Then you can put everything together and multiply them out into a single matrix. Well, in this case, into just two equations. So here, again, what we are relating is the position of the ray at the very end, x2, to the input position of the ray and the input angle of the ray. And this whole thing is basically just multiplied together, those three things that have happened to the ray, right? And the same thing happens to the angle. So you have alpha 2 and all that stuff. Okay? And clearly that's a matrix, right? That's the first term, next term, next term, next term. Okay? So one nice thing about matrix optics also is that you don't need to deal with complicated expressions like this, because you can break up any complicated optical system into a bunch of matrices. And it's also much easier in a computer to actually calculate these. Okay. And you will see this. You've got some examples. So a couple of things that are important in geometrical optics are sign conventions. One caveat is that with respect to sign conventions, it's not a good idea to go blindly. Just assume, just follow the rules blindly. You might have done that in high school or so on, but this is just here for completeness. But you should think about what it means rather than just plug in some signs. Okay. But in the interest of completeness, again, this is not a necessarily a standardized sign convention. This is just something I used for these lectures, right? But what I'm trying to say is that when you look at optical systems, you need to not just do the math, you need to kind of get a sense for what is happening to the light. Okay, so you gotta kind of think a little bit. Anyway, for the purposes of these lights, we will assume the light's always traveling from left to right, which means that we'll measure distances from left to right. So if we say negative distance, that has a different connotation, which means that the light is actually traveling from right to left. Okay, and that will become apparent when you have mirrors. We will talk about mirrors, but we haven't yet. Radius of curvature is positive when the surface is convex towards the light, or towards left in this particular case, so that's assumed like a positive radius of curvature. But if I have that, that's negative. Okay. Longitudinal distance is a positive pointing to the right, so which is what I just said. Lateral distance is a positive one pointing up. So lateral means orthogonal to the optical axis. Again, that's just a convention. And convention is important because remember, when you form real images with a single lens, you'll always have inverted images, right? Your image gets if it's pointing up, it will point down. The image will point. If the object is pointing up, the image will point down. Right? So we'll see that in a minute. Oops. And the angles. The last one is for the angle. Angles are measured in counterclockwise direction from the optical axis, like that, so through the acute angle. Obviously, if it's negative, that means it's pointing down, right? Which is consistent with the negative images as well. Okay. So, for instance, if the magnification of the lens is negative, that means the image is inverted, right? And we'll see that. Okay. So, after the very simple example of air, glass, and just in air, in glass, we will go to the next simplest possible example, which is on-axis image formation. So essentially the idea is that you have a point source, light coming out of it, and you're trying to form a point image. Okay, that's the simplest possible imaging system. And we have something in between. Okay, and we'll see what that is, but you can imagine it's just a lens. So if you ignore that you're within the glass, so in this example you're trying to form the image within the glass. Okay, so Zen is air, let's say in front is glass. Then all you need to do is take your previous equation. So first of all, before we do that, what does image formation mean? We talked about this last time. It essentially means that all the rays that come from S converge to P, irrespective of what direction it came from. That's the point of an image, right? One-to-one mapping, point to point. Right? Now, of course, what that means is that if you take those equations we saw before, we need to make the x2, which is the position of the image, independent of the input angle. Right? So if you recall, the equation here, which represents the whole thing, right, is x2 is what we are interested in. We want to make this independent of alpha naught, right? Which means that any angle the ray comes in, it will always end up at that location. If you have a dependency on alpha naught, that means it won't, right? Won't end up. That means as alpha naught varies, which means the angle going at 0 degrees or 1 degree, x2 will change. It will form at different points. So as simple as that, you try to just get rid of that term. And that's called the imaging condition. Okay? So if you look at this term, by the way, there are two things that are important, right? This distance, DO1, and D12. So that's called the object distance. It's the distance between the object and the interface. Okay, or the lens, for instance. And D12 is the image distance. In this particular example we're going to look at. Okay, because that's the distance between the image and the interface. Okay, everything else is basically the indices and the radius of curvature. Okay, and then we'll see something we are very familiar with. So if you set this to 0, we will get an equation like that. So we set that particular term to 0, and this is something you've seen before. Okay, this is what is referred to as the lens maker's formula. In this, it might be a little unfamiliar to you the way I've written it because I assumed glass. Right? Typically, this is air also. So in this case, n prime by d12 plus n by d01 is n prime minus n by r. Okay, couple of things. Of course, if I can make n prime equals to 1 as well. We'll do that in a second. But that's only valid as long as you have a lens there. And we'll see that in a minute. The other thing to remember is that this term is what's called the power of the surface. Okay? It is essentially how sharply can it bend the ray. It's a measure of how sharply you can bend the ray. Okay? It's essentially proportional to 1 over the radius of curvature. So more radius of curvature means you have a bigger curvature on your lens, the more sharply it will bend the rays, right? which is common sense, right? And they're measured in diopters. And those of you who wear lenses are probably glasses are probably very familiar with this, because that's how the power is measured. Okay, units are 1 meters. Okay, we'll relate this to something more familiar in a minute. Actually, here. So what happens when DO1 goes to infinity? So what's the image of the point object to infinity? Again, you've seen this in high school physics, I believe. If you take the point object and move it to infinity, you will focus to a point which is called the focal focus of the lens, or focus of the surface in this particular case. Right? Or the focal length. And in our case, we can just take that. If you set DO1 to infinity, that term goes away, 1 over infinity is 0. And then you can very simply say what D12 is, which is now the focal length of that surface, right? Which is nothing but n prime r time divided by n prime minus n. Okay? It's also referred to as the back focal length. We'll talk about this when we talk about lenses because it's on the other side. In my convention, I remember going from right to left to right side. Okay? Okay. You can do the opposite also. What is the condition? Where should the object be to form the image at infinity? Okay? So that, for instance, there is, if you just look at the equation, clearly, clearly if this goes to infinity, which is this image, then there is some object distance that makes it happen, right? And that's called the object focal length in this particular case, or it can be called the front focal length in the case of a lens. Okay, so a point object there, after refraction, basically becomes parallel to the optical axis. I assume you guys are familiar with the idea of parallel rays intersecting at infinity, right? That's the definition of parallel rays, right? Which means they don't intersect, essentially. Okay. So we can summarize this this idea of matrices very quickly. So metric formulation, which is essentially what I wrote here, except that now I have a refractive index term, and I switched the variable. So this is what I was checking, but I guess I messed up here. But here the angle is the first variable, and the position is the second. But otherwise, everything else is the same. And I've introduced the refractive index. It just simplifies the matrix terms, but you can imagine it just comes from the equations, right? So you have that's what you're trying to calculate. That's a matrix that represents all the transformations that has happened to the ray, and that's the input. Okay, is that clear so far? It's the same thing that we have done so far. It's just that we have put the index, refractive index, to represent the medium. Okay. So translation through a uniform medium is very straightforward. So alpha 1 is essentially alpha naught, right? It's the same thing, nothing changed. And straight line, so that's 0. And x1 just shifts up by the tangent, right? So it's just d naught 1 over n. d01 is the distance that it has traveled. Okay. There's a factor of n because of that n. So you have to kind of cancel those two out, right? So it's very straightforward stuff. Okay. Same thing you can do for the refraction by spherical surface. And when you write it this way, you can see that this term m12 is now the power of the lens. You have a negative sign there also. It comes with an equation. Okay, and it becomes important in a few minutes. Okay. So if you like I said before, in order to calculate what happens through the spherical surface, again, just to summarize, you can just multiply the matrices together. So if you have a matrix for translation through air, which we just did, and you multiply that by refraction and spherical interface, and multiply that by translation through glass. Now, if you switch one of these, clearly the answer will be wrong, right? So you have to follow what happens to the ray, because matrix multiplication is not commutative. Okay, and when you multiply these, all these three matrices together, you get these two sets of equations. Again, straightforward stuff. Okay, now we move on to lenses, which is more realistic because you don't form images inside glass. You want to form images in air, typically. So that means you need to have two interfaces. Right? You have an interface from air to glass and then back from glass to air. And to analyze this is exactly the same way as we have done. Right? So now you guys should be able to do it by yourself. And in a thin lens, and we'll talk about a thick lens for a second, in a second, we assume that there is no propagation within the glass. Only two things happen in a thin lens. Refraction of the first spherical interface and refraction of the second spherical interface. Obviously, that's an approximation, that there's no lens which is like that. Right? But we'll talk about thick lenses, but this is easier to understand. Okay, so you can define the matrix transformation of a thin lens by just this matrix. Right? Very simple. So we already know what these are. We know what this is. We know what that is. We can plug them in, multiply them, then we know what a lens does. Thin lens does, anyway. Okay? Very straightforward. So if we do that, so that's what the first spherical interface is, going from air, 1, to glass, n prime, with the radius of curvature r prime. That's the first. So let me step back. This is actually an important thing in terms of order. Wait a second. Yeah, these are okay. So these are mistaken. I will correct them. Let me just clarify one thing. This is the first transformation that happens to the ray. Okay, in terms of, because remember when you do matrix multiplication, you multiply the first matrix to something, and then you multiply the next matrix to something. You always go from right to left. Right? Okay, you have to think about this a second. It is important, actually. In other words, I made a mistake here. This should be translation through DO1, not D12. So that's the first thing that happens to this ray. Right? Then you have refraction at the interface. Then you have translation through the glass, which should be D12, not D01. So these two things should be flipped. If you don't, you won't get this answer, essentially. Okay? I will correct this, and I'll repost it. I already have. Same thing here. I made a mistake here as well. Right? This should be the first thing that happens to the ray, which is refraction of the first spherical interface, if I call that the first interface. And then you have the refraction of the second spherical interface. Right? It's a little bit confusing until you do it a few times, when it becomes natural. Okay? The key to think about it is think about what happens to the light as it propagates through the system. Okay? The first thing that happens to the light should be the first matrix that you are sitting next to. So imagine that's the starting point. This should be the first thing that happens to the light. Once you have that, then it's just a matter of following what happens, right? Straightforward. Okay, so with that in mind, we can just write these things out. So of course, this is the first thing that happens to the light, which is refraction at this spherical interface with this power, right? So it's minus n prime minus 1 over r. Not r prime, which is why I caught it. So I was looking for the r. Okay? And then you have the same thing, but now you have R prime. Of course, the ends are changed also because now you're going from glass to air. So this becomes 1, that becomes something. Other than that, everything else is the same. Okay. Some of these are just subtle things, and you should just look at it, make sure you're clear on what is happening. Okay. And you probably have to go back and think about it at home. So I would recommend thinking about. I mean, you've seen this before. It should be pretty straightforward. But some subtle things are requires a little bit of thought. So just think about it. If you're still confused, make sure you come talk to me. Okay. So it should be very clear to you. Okay, so you can multiply them out and you get something like that. Okay, and this is what's called the lens maker's formula actually. Why? Because you form images in air. Okay, sorry, the lens maker's formula is when you apply the imaging condition to this actually. So that's the matrix transformation of a thin lens. If you put this as this is the power of the lens, right? This is power, n prime minus 1 times 1 over r minus 1 over r prime. This can also be called the lens maker's formula, but the imaging condition is also referred to as the lens maker's formula. This is again from a few hundred centuries ago, right? When people used to make lenses this way. But we'll come to that also in a second. Okay, so the one interesting thing to also keep in mind here is that the top right element in each of the matrix represents the power of the surface. So for each of these matrices, that represented the power of the spherical surface, right? And this one represents the power of the lens. And we will see when we do this for the thick lens, this term, not this particular term, but that term that is positioned there represents the power of the thick lens. And that's in general true. And any thought on why that is, by the way? Well, what is that term? What is this term? It is the dependence of the position on the angle, right? It's essentially what power is. You're trying to bend the light. As at the angle, you want to bend it more. Or less, I mean, depending on what the power is, right? I'm just trying to abstract some intuition from the math, which is not necessarily very intuitive. You have to kind of think about it. Okay. So far we have just looked at this mathematically, but from a qualitative perspective, what we also need to keep in mind is that you can have many surfaces for lenses. And different surfaces have different powers, right? And again, you've seen this in high school, I believe. If you have positive power, the rays are bent toward the optical axis. If you have negative power, the rays are bent away from the optical axis. Again, something you've seen before, but keep that in mind. In a plano-convex lens, now why is it called a plano-convex? It is a plane on this side and a convex surface on this side, and this is the most common lens that you will see if you go into an optics lab or something. Okay? The radius of curvature on this side is positive, based on our sign convention, right? That's what we said. What is the radius of curvature of this?
0.
Yeah, it's a plane, right? So radius is 0. And the light bends down. And the biconvex lens just has convex surfaces on both sides. On this side, the radius of curvature is positive. On this side, the radius of curvature is negative. Why? Right, it's concave to the light, right? Concave to the left, essentially. Although we call it convex because we only see the outside, right? Yeah, go ahead.
The plane would have an infinite radius.
That's correct. Sorry, yes, that's correct. No, wait a second. Yes, the plane will have the radius of curvature infinity. That's correct. Correct. Right. The way to think about it. So, okay, I misspoke about something also, which I should clarify. I'm thinking too fast. So, if you think about it, the radius of curvature being large means the surface is more plane, right? Because the way to think about it is, from very simple geometry, is basically, okay, anyway, is, let's say you have a surface here. When I say a spherical surface, it has a center here, right? That's how you draw a circle or sphere or whatever. And that's the radius of curvature, right? Now, if I make the radius of curvature very, very, very large, at some point it will become flat. So, right? Now, of course, when the radius of curvature increases, the power of the surface decreases, right? A flat surface has no power, basically. 0, because the power is inversely proportional to the radius. Which actually I did say correctly, but that was what I was trying to correct. But I remember I said that right. The power is always inversely proportional to the radius. So if R goes to infinity, you can see that's 0, basically, right? Okay, so for the negative power, it bends it outward, and you've seen this before. There's a plane of concave lens. If you have a concave surface, then the radius curvature is negative because it's concave to the right, concave to the left. Okay, same, and this, of course, radius curvature is 0. And if you can have a biconcave lens, also that's the same thing. Of course, there are reasons why sometimes you have planar concave versus biconcave. Sometimes it has to do with fabricating the lenses, how you make them. It's much easier to make this as opposed to make that. Cheaper. Why? Because you have to shade two surfaces here. You only have to shade one surface. Right. Okay, we'll see some examples there. So this radius of curvature is negative, that radius of curvature is positive. Why? Because that's convex towards the left. So all of this is consistent with the sign convention that I put forward earlier. Okay? Again, kind of keep that in mind. Okay. Oh, also this is just a summary. In the matrix formulation, the power is minus M12. Now the negative sign we'll talk about in a bit. Well, it'll become more apparent in a bit, but we saw it here. Negative power means it bends it out. Positive power bends it in. Okay, so this sign is actually important. So when I say M12, it refers to the matrix. Okay, so the effect of an optical system in geometrical optics, any optical system can have 100 optical elements or 1,000 optical elements. Can all be summarized into one simple matrix. One single matrix, sorry. May not be simple. 4 terms. Okay? And this term refers to the power. It's a negative with power. Okay? And the focal length of the system is related as 1 over the power. Clearly, this is only applicable for imaging optics. We'll talk about non-imaging optics later, but okay. Is that sort of clear? I mean, you see how it can be done, right? So you have 100 lenses, which are spaced in particular distances and so on. You can write a matrix for each of the lenses, and write a matrix for what happens in between the lenses, just free space propagation. Multiply them all together. You can have 150 matrices, right? Or 200 matrices. At the end of the day, you'll end up with that, right? One matrix. It's clear, right, how it can be. And that's exactly what software does. And we'll talk about some simulation software in this class. Actually, I think not next week, but the week after. Okay, so a few other notations that you should be familiar with, when we talk about optical engineering are principal planes and cardinal points, and we'll talk about those. So we've already seen the focal points, which is essentially a point on the optical axis. If you place a point source there, its rays, after it passes through the lens, becomes parallel to the optical axis. It's the same, we did this for a spherical surface, but it's the same for the lens. Same thing happens for the lens. Okay? And that's called the first focal plane, or the front focal plane of the lens. Okay? Then if you have a ray that comes in from infinity parallel to the optical axis and it gets focused on the other side, same as we talked about before, and that's called the second focal plane or the back focal plane. Okay? And it's called a focal plane because you can have a situation where the rays come in at an angle. but still parallel to each other. So let's say that's the optical axis. We have a lens. Okay, if you have a ray that comes in at an angle, okay, you will still form a focus on the focal plane, but off the optical axis. You'll form a focus here. Okay, and you can do all this with the matrix optics we talked about under paraxial approximation. When this angle goes to 0, the point moves up here and it goes down and moves up there, so it just shifts. Okay. This is actually will become important later on. Because you can imagine, light from the sun, sun's basically at infinity compared to any distances of interest here, right? So you can imagine that sunlight. As the sun moves, this angle is changing. So what happens at the focus? Basically moves up and down, right? Very simple. Okay, the other planes that are of interest are so-called principal planes. Okay, the principal plane is not terribly important for us for the class, but something you should be aware of. It's essentially an abstraction. So if you purchase a lens, if you look at the stock of a lens, it will tell you what the principal planes are, what the focal lengths are, and so on and so forth. The principal plane is essentially a mathematical abstraction. It tells you if you were to draw a ray, so let's say starting from the first focal point on axis, at the first principal plane, you can make it go parallel. So if you were doing ray tracing by hand, okay, if you knew where this plane was, you can simply draw that and that for any complex optical system. So let's say this can represent 1,000 lenses. So it's another way of doing, when we say a matrix can represent 1,000 lenses, you can use two principal planes to essentially represent what happens to raise 1,000 lenses, many lenses as well. So it's a way to do ray tracing drawing. Okay, so it's just a plane where the ray that comes in from one side intersects with the ray that goes out from the other side. It's as simple as that. Okay, and its location can be different based on what are the details inside here. It will become clear in the next example. It's a little bit confusing. And the second principal plane is essentially the same thing, but on the other side. And you are focusing right. Okay. Okay, so this is also an important consideration. In paraxial approximation, the focal planes and principal planes are flat, they're planes, but in reality they're curved surfaces. We have called spherical aberrations, which shift the focus. Okay. In other words, when the sun moves, this point is not necessarily going to follow a line. In reality, it's going to follow a curve. Okay. Something you're going to have to keep in mind later on. Okay, we'll again come back to that. Okay, so this is just the definitions. So in this example, remember, I've drawn a thick lens. So in a thick lens, the only difference is that instead of just having two interfaces, I put some glass in between. Made it thick. So you have propagation inside glass, essentially, right? So you have these things which we defined before. You have the front focal length, which is the distance from the first focus to the first interface. And then you have the back focal length, which is the interface of the distance between the last interface and the back focus, or back focal plane. And then you have what's called the effective focal length, okay, which is different, which is the distance between the principal plane and the focal plane. And all three of these things can be quite different depending on the details of the lens. Okay? And we'll see how they vary in a little bit. So again, just the significance of the principal plane is that you can take a very complicated optical system and replace that in just as an abstraction by just a plane. Which means if I have a ray that comes in parallel to the optical axis, if I know the location of this plane, I can predict exactly where it will focus. of any complex optical system, as long as I know where this plane is. So that's the advantage. Okay, it's another tool, just like we did for the matrix, right? Any complex optical system, you can still write a matrix, right? M1, M2, M3, M11, M12, M21, M22. So the principal planes are just another tool. And the same thing for the first principal plane. If I knew exactly where that is, I can take this away, and I know exactly what happens if I place an optical a point source in the first focus. I mean, I can draw this ray. Okay. In other words, the question is the following, right? If I put a point source there, what happens to it? What happens to the rays? Is what I'm trying to answer. Okay? If I know where the principal plane is, I know exactly it will intersect here and it will become parallel to the optical axis. And every ray will do that. Every ray, irrespective of the angle. That's the advantage of the principal plane. Okay? Now, coming back to the matrix formulation for a thick lens, again, fairly straightforward. We have refraction at the first interface, propagation through the glass, and refraction at the second interface. Put the three matrices together, you get a matrix for the thick lens. Pretty straightforward, right? So again, the first matrix is the first interface, R1, see? And then your propagation through the glass, and then your R2. Same matrices that we've seen. Multiply them all out, and you get a single matrix which represents the lens, thick lens. Okay? Again, this term is the power of the thick lens. Negative is the power, but okay? And you get a few other extra terms here as opposed to a thin lens, primarily because you have this propagation of glasses, so you have these D, L terms everywhere. L for lens. Okay. Other than that, it's pretty straightforward. Power is 1 over the focal length, so you can write 1 over the focal length is that term, M12, which is nothing but this one right here. Okay. So you can write that down, and that is what is referred to as the effective focal length. Not the first or the second, or the front or the back, is the effective focal length. Okay? Now, effective focal length is the distance between the focus and the principal planes. Okay? A little bit different than the focal length that front focal length or the back focal length, where those distances are measured from the interface themselves. Okay, so again, if you put DL equals 0 here, you will get the same thing as the thin lens, which is just that. So you just have an extra term. Okay, pretty straightforward. Now, we can do the same imaging condition that we applied to for the thin lens. Again, remember for the thin lens, all we did was we just set this term to 0, right? Wait a second, what did we do for that? No. We said, sorry, this should be independent of that. So which term is that? Is that it? Right? The position should be independent of the angle. That's what we said. So it should be this first term should go to 0. Right? That's the imaging condition we did before. I remember earlier I had flipped the variables when I wrote on the board. Okay, so we can also do it just by drawing with the principal planes. So you can see if you have an object here, and you're forming an image there, you take one point of the object and draw rays from it. And the idea of an image formation is that all those rays will end up at one point of the image. Right? That's a definition of image formation. You have one ray which passes through the first focus. Once it intersects the first principal plane, it becomes parallel to the optical axis. So we can draw that as long as we know the principal planes. Okay. Next, let's say we draw a ray which is going parallel to the optical axis, and let's say we know the second principal plane. Once it intersects that, it passes through the second focus, or the back focus. And where this ray and this ray intersects, we know that is the image point. Okay? So now you know exactly where the image point is. You only need two rays, right? And they intersect. In fact, you've done this in high school physics by hand. Okay? Of course, in high school physics, you didn't talk about principal planes. You just drew a lens and drew these things. You can also draw what's called the chief ray, which passes through the point that intersects the optical axis and the principal planes. And the definition in that case is that the ray that comes out also comes out in the same angle and from the same point at the intersection of the second principal plane and the optical axis. And by definition, that also has to pass through the point of the image. That's the imaging condition. Now, all of this should be very familiar to you if I just replace those principal planes with a lens. So if I just put a simple lens here and I have an object here, if I draw that, and you've seen this in high school, right? We've done this. And if this is my focus, okay, and this is now the chief ray, as is the center of the lens, right? It's exactly the same thing as what I'm showing there, except that this is a single lens that can be any complicated optical system. And the principal planes for a single lens, the first and second planes both coincide, and it's just that. That's why it's simple. Okay? Okay, so let's see, what did this say? So the image point is located at the common intersection of all rays emanating from the corresponding object point. Rays passing through the two focal points and the chief ray can be ray traced directly. So that's basically what we just draw. Okay, now we can do this, of course, in matrix form as well, which is sometimes easier. The system matrix can be defined as follows in this particular notation. Let me walk you through it quickly. We have an S, which is the object distance. So it's the distance between the object and the first principal plane. Okay. Now, when object distance can also means other things, but this is how I'm defining it. So usually people will tell you what that is. Okay. Then you have an S prime, which is in this case is referred to as the image distance, the distance between the image and the second principal plane. Okay. Now you can plug in the matrices. You have this matrix for propagation in air from the object to the first principal plane. Okay. Then I have this for the power of the optical system. Okay. And then I have this for propagation outside the optical system from the second principal plane to the image. That's the most general way to represent anything, if you know the principal planes of an optical system. Okay. Of course, the power of the system is basically embedded into the, it's calculated from the details of what the optics are, right? What curved surfaces, how many curved surfaces, where are they located, all that stuff. You multiply them out and multiply all those matrices out, and you get this particular one. Then when you multiply all three of these out, you get that. And that represents the system matrix for any complicated optical system where only the principal planes are given, basically. Which could be the case, okay, if you have a very complicated system. And of course, the imaging condition is we've seen before. We just take the term, like I said, the variation of the dependence of x prime on alpha should go away, essentially, right? This imaging condition. So we set that to 0. Right? X prime must be independent of alpha. Once we do that, we get the imaging condition, which is the same as before. Or same as what you've seen before, actually. We haven't talked about it. It says n over s. N is the refractive index here, which if it's the air is just 1. Okay, n prime over s prime. Again, n prime is the refractive index here, which if it's air is also 1. okay, is equal to the power P or 1 over F. And F is the effective focal length. So if it's in air, it's 1 over S plus 1 over S prime is 1 over F. This is also referred to as the lens maker's formula. So if you know the focal length of your lens, if you know where the object is, you can calculate where the image is. Image will be 1, right? So one way to gain some intuition into this is to think about a few things, right? So extreme cases. So what happens if S goes to infinity? S prime becomes equal to F, right, from this equation. So in other words, if your object is at infinity, which is where the sun is, for instance, your image is essentially the focus. The farther your object goes away from the focal plane, the closer your image gets to the focus. Not only that, it also gets smaller. Right? You can kind of imagine that. If this gets further away, if this gets closer to the focus, it has to, at the end of the day, it has to become a point. So it has to get smaller, the image. Okay? Same thing happens on the other side. If your object comes closer and closer to the focus or focal plane, your image goes farther and farther away, and it blows up, right? It gets larger and larger. Does anyone remember what happens if the object is closer than the focus? What happens if it passes the focal plane? What happens to the image? No, it will remain underneath. I mean, it is flipped. That's correct, actually. But that's actually wasn't what I was looking for. What happens if the object is very close to the lens? I mean, you've seen this before.
Blurred.
Blurred? No. Let's say an image is formed. I mean, blurring. Okay, so one thing to keep in mind. When you say blur, typically what people mean is that you're not at the right plane. So you're a little bit away from the image plane. So then you form a blurred image. And once you get it into the right plane, it becomes a sharp image. Move away, it becomes blurred. Okay, that's what you will see. So if you place a piece of paper here and move it around, that's what you will see. My question is different. My question is what happens when your object goes in here, in between the focal plane and the lens. Actually, let's take an example of a lens. Maybe you're familiar with this principal plane notation, but let's take the case of a very simple lens. Okay? And let's mark the focal planes here. The symmetric, so they're exactly the same. What happens if you're an object here?
Is it magnified?
That's correct. Yeah, but not just that. It is virtual, exactly. So remember real versus virtual images. A real image essentially means the rays actually physically intersect. Okay? We'll see what a virtual image means in a minute. Another way to think about it, real image is something you can see on a screen. So you take a piece of paper and put it right there, you will see it on the piece of paper. The virtual image you won't. You'll see in a minute what that. So let's try to draw the virtual image. Let's try to draw what happens. And this, again, you've done this in high school, but let's do it again. Okay? The simplest way to draw, okay, let's draw the first ray. Let's imagine a ray coming in straight, parallel to the optical axis. What happens to it? It just passes through this, right? Through the focal point. Okay, that's straightforward. Next ray, let's draw the chief ray. So it passes through the center of the lens. Nothing happens to it, just goes straight through. That's the so-called chief ray, right? Passes through the center of the lens. For a thin lens, nothing happens to it, essentially. Okay, do you see where is it going to intersect? It's not going to intersect. You only need two rays to find where the image is, right? Really. This is not going to intersect anywhere. So it doesn't form a real image. But if you look from this side with your eye, okay, you look from the side, you will still see an image. And the reason is because your eye has a lens in it. It will take these rays and form it'll focus to your retina. In other words, your eye will imagine an image on the other side of the lens, which is formed by basically taking the rays back. Okay? Clearly, if you put a screen there, you won't see anything, right? Obviously, right? You're behind the object and you're behind the lens. But if you look, you will see it. Right? I mean, you have seen this. I mean, take a lens and take a look at it. You will see what I mean. And you've seen this in high school, I'm sure. Okay, the two things to keep in mind, it's virtual. Three things to keep in mind, it's virtual. It's in the same direction as the object. It's not inverted. Right? And lastly, it's magnified also. But magnification can happen in real images as well. Okay, so kind of keep that in mind. And now, I guess more importantly, you can predict this from matrix optics as well, right? And the way you would know this is if the image distance becomes negative. Because remember, the image distance is measured in that direction. If that becomes negative, that means it's behind the lens. And it can happen, right? You can have a situation where f is negative. That's easily possible because you have a lens with negative power. And your s prime, s is the object distance, is very small, meaning it's very close to the lens. And this thing can be negative. Okay, so another way to think about it, if this is this very small, which means the object is very close to the lens, this whole thing becomes very big, right? If this whole thing becomes bigger than that, clearly that must be negative, right? But common sense, now you know this. Okay, so anyway, so go back and think about it. We should finish a couple more things before we wrap up. First is the lateral magnification. Magnification is essentially the size of the image with respect to that of the object. So magnification, in this case one-dimensional magnification, is defined as x prime divided by x. Quite simple. And from simple geometry, we can prove, and I won't go through the detail, that it's also equal to 1 minus p s prime over n prime. Okay? And that essentially comes from the imaging equation. Another way to look at it is, obviously that's x prime, that's x. It's also true in the case of virtual or real, it really doesn't matter. X prime by x is also given by this geometrical relation, okay, of similar triangles. Again, you probably have seen this in middle school or whenever you guys learn this stuff. Right? That angle is the same. X divided by this distance, s, is equal to tan of that angle. That is the same as x prime divided by s prime. Yeah, very simple, right? So if I write that down, x prime by s prime is just x over s. So magnification given by x prime by x is just s prime over s. So the ratio of the image distance to the object distance gives me magnification. So you want to magnify the object, what do you need? Sorry, if you want a huge image, real image is called, compared to the object, what do you need to do? Can someone tell me? Let's say I want x prime to be 10 times x. In other words, I want to make an image that's 10 times bigger than the object, which is, for instance, what you want to do in a microscope, right? That means my image distance must be 10 times as the object distance. The real image, that means I need to be far away. The image will be formed far away. The opposite if you want to do demagnification, which is sometimes required. Okay? In a virtual image, obviously this is different. Becomes negative. right? S prime is now negative. Right? Okay, so let me see what's next. Yeah, okay. I think I'll stop here.